In this lecture, we should introduce another abstraction device, namely modules. A module consists of functions that are related to each other and defined in a single file. The name of the file must match the name of the module. The module can be used in any other file in the same directory by using the command import, as we shall see later. Here is an example of a Q module. The Q module is defined in the file q.hs. The first line is as follows: module Q within parentheses the names of many functions where, and then you give the definition of functions and data types as usual. Module Q within parentheses, I have given the name of the constructor new Q. Notice the special syntax. You have to say new Q followed by parenthesis, and within parenthesis you put 2 dots. And then these are some other functions that I want to be visible outside this file: empty, isEmpty, enqueue, dequeue, show, etc. The definitions of empty, isEmpty, enqueue, etc. have already been presented in the last lecture. We can use the Q module in another file in the same directory by adding the line import Q. A module acts as a hiding mechanism. The internal representation of the data types can be hidden from the outside world. Only those functions listed inside the parenthesis in the module statement are visible to another file when it does an import Q. This means that auxiliary functions can be hidden from users of the module. Let us look over Q module in more detail. Our Q is not abstract enough since the internal representation is visible outside. Recall that the Q is represented in terms of 2 lists, one half of the list and the reverse of the rest of the list. We can fix this by hiding the constructor. In this new declaration, the new Q function is not exported. Instead, we have a make Q function which takes any list of elements of type A and produces a QA. The new declaration is as follows: module Q, make Q, empty, isEmpty, enqueue, dequeue, show, etc. where data QA is as before new Q list A, and we have a new function make Q which takes a list of objects of type A and returns a QA. Make Q of L is nothing but QL empty list. The other functions are as before. Empty just returns a Q which is empty, new Q, empty list, empty list. IsEmpty will check whether a Q is empty. IsEmpty, new Q of empty list is true. IsEmpty, new Q of anything else is false. Enqueue X of new Q, Y's and Z's is new Q, Y's, X colon Z's. Recall that we add X to the head of the second list. Dequeue of new Q, X colon X's and Y's is nothing but X, comma, new Q of X's and Y's. Recall that in a dequeue we remove the element from the head of the first list, and if the first list is empty, then we reverse the second list into the first list and extract the first element. So dequeue of new Q empty list Y's equals Z, comma, new Q of Z's and empty list, where Z colon Z's is reverse of Y's. One can also add instance declarations inside a module. Here we see that as before, we are declaring QA to be an instance of the type class show, provided A itself is a member of the type class show. Instance show A implies show QA, where the show function on new Q, X's and Y's is just show of some fancy characters plus print all the elements of the Q, print elements of X's plus reverse of Y's, plus close the braces. So in our representation, we have a brace followed by a square bracket, followed by all the elements listed in order, followed by closing the brackets and the brace. Print elements is a function from list A to string, provided A is of type show, belongs to the type class show. Print elements of empty list is the empty string. Print elements of the singleton list X is nothing but show X. Print elements of X colon XS is nothing but show X plus, in this case we have an arrow, plus plus print elements of XS. So one uses the queue module by adding import queue at the start of a file before defining any functions in that file. When we do this, the constructor new queue and the function printlms are not available outside of queue.hs. The constructor new queue we are not making available externally because we want to hide the internal representation. And printlms is just some helper function that we need in order to define show. So therefore there is no need for it to be visible outside the queue module. One creates new queues by invoking the make queue function. For instance, you might say new queue equals make queue of the list 1 to 100. Here is another example, a stack module. Module stack, there ought to be two dots here. Stack, this is the data constructor, and we have empty, push, pop, is empty, show, etc. We are exporting all these functions, and the definitions are as before. Stack A is nothing but stack. This is the value constructor, and then you have list A. Empty equals stack of empty list. Push of X in stack XS is nothing but stack of X colon XS. Pop of stack of X colon XS equals X comma stack of XS. Is empty checks whether a stack is empty. If on stack empty list it will return true. For stack anything else it will return false. Similar to queues, we can also add instance declarations inside the stack module. Instance show A implies show stack A, where show stack L equals print elements of L. Just like in the queue example, here again we are printing the elements with arrows in between. This is exactly the same as the print elements function that we had earlier. Let us see an extended example of using stacks. In this example, we'll try to compute the value of postfix expressions. A postfix expression is an arithmetic expression where the operator appears after the operands. Importantly, no parentheses are required in a postfix expression. Here is an example. 3, 5, 8 star plus is a postfix expression, and the way to interpret it is that this star occurs after two numbers. So we have to take this as a sub-expression. This is the sub-expression 5, 8 star, which stands for 5 into 8. Then we have a plus following a string of numbers and operators. This is to be interpreted as the plus operator applied on the previous two expressions. The expression previous to plus is 5, 8 star, and the expression previous to that is 3. So this whole thing stands for 3 plus 5 into 8, 43. Here is another example. 2, 3 plus 7, 2 plus. So this plus occurs after two numbers. So this is to be taken as one expression, 2, 3 plus, which stands for 2 plus 3. 7, 2 plus, this stands for 7 plus 2, which is 9. And then there is a minus. This stands for there are two expressions preceding the minus. So it is the first expression minus the second expression. So 2, 3 plus is an expression, 7, 2 plus is an expression, and this expression followed by that expression minus is another expression, and it stands for 2 plus 3 minus 7 plus 2, namely minus 4. Every bracket free expression can be converted uniquely to a bracketed one. That is the speciality of postfix expressions. The way to do it is to scan from left. If it is a number, it is a standalone expression. If it is an operator, you bracket it with the previous two expressions. So 3 is a standalone expression, 5 is a standalone expression, 8 is a standalone expression. You encounter a star, and this creates a new expression which is gotten by bracketing this with the previous two expressions, namely 5 and 8. So 5, 8 star becomes a new expression. When you reach plus, you have two expressions before it, namely 3 and 5, 8 star. So you bracket this plus along with those two. Similarly, for 2, 3 plus 7, 2 plus minus, 2 is a standalone expression, 3 is a standalone expression. When you encounter the plus, it creates a new expression which is the previous two expressions bracketed along with plus. So you get 2, 3 plus. You move on, 7 is a standalone expression, 2 is a standalone expression. When you encounter the plus, 7, 2 plus becomes an expression. When you encounter the minus here, it is to be grouped with the previous two expressions, which is 2, 3 plus and 7, 2 plus. So ultimately you get a value of minus 4. We shall now consider how we can automatically evaluate postfix expressions. We can just following the bracketing algorithm and use a stack. Here is how it proceeds. Scan from the left. If it is a number, it is a standalone expression, so push it onto the stack. If it is an operator, you have to apply the operator to the previous two expressions, and the strategy we follow is that we push all expressions onto the stack. So we remove the top two elements of the stack, which correspond to the two expressions that this operator has to be bracketed with. You apply the operator on the two expressions and push the result onto the stack. This is the overall strategy. Now we will have to use a stack module and implement this algorithm. Here is how we would program this calculator to calculate the value of postfix expressions. A postfix expression is given as a list of integers and operators. Since it's a list of a mixed type, we need to create a new data type. We will call these tokens. A token is either an integer or an operator. Here is the definition. Data token equals, it's either an integer given by the data constructor val, or it's an operator, and we denote the fact that it is an operator by using the data constructor op. If it's an integer, it has a parameter which is of type int. If it is an operator, it has a parameter which is of type char. And importantly, we need to import stack before we program this calculator. And we can define a type synonym for list of tokens. Type expression equals list of tokens. So an expression for us is just a list of tokens. Recall that our strategy for evaluating an expression is to read the expressions from left to right, and when we encounter a number, to push it onto a stack, and when we encounter an operator, to apply the operator on the top two elements of the stack. This leads us to the function eval step, which is one step in this computation. Eval step is a function that takes a stack of integers and a token as input and produces a stack of integers as output. Eval step st of val I equals push I st. Recall that val is a data constructor that indicates that the token that we have encountered is a number, an integer, and the integer is given by I, which we push onto the stack. Eval step st op c. Recall that op is a data constructor that indicates that the token that we have encountered is an operator, and the operator happens to be c. And for simplicity, we will assume that c is either plus or minus or star. The definition is as follows. Eval step of st of op c is push v2 plus v1 onto st2 if c equals plus. Here v1 is the value on top of the stack given by pop st, and v2 is the value that is second from the top of the stack, which is given by pop of st1. Recall that pop is a function that returns a pair, the top element of the stack and the stack that you obtain from removing the top element from the stack. So st1 is what you get if you remove the top element from st, and st2 is what you get if you remove the top element from st1. So v1 and v2 are the top two elements of the stack, and st2 is the stack that you obtain after you remove the top two elements. So you remove the top two elements from the stack, add them and push them onto the stack. So push v2 plus v1 onto st2. If c is minus, then you have to push v2 minus v1 onto the stack. Recall that if you encounter something of the form 3, 5 minus, what you intend is 3 minus 5. And when you encounter 3, 3 would have been pushed onto the stack, and when you encounter 5, 5 would have been pushed on top of 3. So the second element from the top is v2, and you have to subtract the top element from the second element of the stack. So you have to push v2 minus v1 onto st2. If c equals star, then you do push of v2 times v1 onto st2. Once you have defined eval step, we can actually evaluate an expression. Eval expression is a function from stack of int to expression to stack of int. So it's a function that takes two arguments as input, a stack of integers and an expression, and it produces a stack of integers. Typically, the stack of integers that an expression takes is the empty stack. So eval expression of st empty list, this denotes that there is nothing to be done with the expression, is pop st, but recall that pop st returns the top of the stack and the remainder of the stack, and first of pop st will be the top element of the stack. Eval expression st and t followed by t's, t is a token followed by another bunch of tokens, is eval expression of eval step of tst and then ts. So this eval step of tst modifies the state of the stack st by taking into consideration one token t, and what we do is we evaluate the rest of the expression, namely t's, on the modified stack. So this is how we define the calculator module based on the stack module. After having seen a non-trivial example, we shall consider some more features in modules. One thing to remember in modules is that the functions that we provide in modules ought to be as general as possible. We should not make any assumptions about how the functions would be used by other modules that import this module. Here is an example. Consider the function max, which tries to find the maximum of a list of integers. Max is a function from list int to int. So max of the singleton list x is just x. Max of x colon xs is x if x is greater than y. Otherwise it's equal to y, where y is nothing but max of x's. So this max should not be confused with the built-in function max, which takes two integers as arguments and produces the larger of the two integers. We use the name max here for simplicity. But in this definition, what do we do if, what is the case that we have to use for max of empty list? One option is to define max of empty list to be some default value like -1. -1 is a default value, and it works if the input list contains only non-negative integers. Then this -1 serves to indicate that the list that was input was empty. But what if the input list could also contain negative numbers? Then this option doesn't work. We might have to provide a different default. Another option, which is slightly more robust, is to define max of empty list to be error empty list. Error is a function that is of this type, string to a, any type a whatsoever. It is a function that takes an error message as a parameter and it just causes an exception. It prints the error message out on screen and aborts the execution. So this is slightly more robust than what we had earlier, because if we default to -1, then if your input list does contain negative numbers, then you do not know whether a -1 was returned because the list was empty or because -1 was actually the maximum in the list. But even this is not very desirable because the error function actually aborts the execution. We want something that works on most inputs and it also doesn't abort execution. The point is that we have no idea what the context is in which the function would be used. In these cases, one can actually use the built-in type constructor maybe. Maybe is defined as follows: maybe a equals nothing or just a. So no matter what type a is, you can, if for instance if a is int, you can build a type maybe int, which is given by nothing or just int. Here is how we use it. Here we define max to be a function from list of int to maybe int. This is inside the module. Max empty list equals nothing. Max of singleton x equals just x. Max of x colon xs is if max of xs is just y and x is greater than y, then max of x colon xs is just x. Otherwise, it is just y. This is how we would define this max function to return a maybe int rather than just an int. And outside the module, we might have a routine like print max, which takes a list of integers as input and produces a string as output. Print max of L is in case max L is nothing, then show the empty list. In case it is just x, then you show maximum equal to plus show x. This is a scenario where we leave it to the user of the module to use the function in the appropriate manner. So therefore, we should neither return a default value assuming the type of usage of the function, nor should we abort. Here we see that even in the case when the list is empty, the print max routine would like to print something meaningful rather than just abort. Here is another example of the use of maybe. Consider a table data type that stores key value pairs. Type key is just integer, let us say, and type value is just string, let us say. So type table is just list of key value pairs. We want to define a function myLookup, which is a function of type key arrow table arrow maybe value. What it does is to look up the value corresponding to the key in table if key occurs in table. If key occurs in table, it will print the corresponding value, otherwise it will return nothing. Here is the definition. MyLookup of k empty list is nothing. MyLookup of k and k1 v1 followed by kv's is if k equals k1, you return just v1. Otherwise, you do a MyLookup of k in kv's in the remainder of the table. Actually, this behavior is given by the built-in function lookup, whose type is EQA implies A arrow list of pairs A comma B arrow maybe B. This is more robust than returning error or some default value on the absence of the key. To summarize, we have introduced modules and shown how you can hide implementation details using modules. We have seen the examples of stack and queue modules. We have seen how to use the stack module to do some non-trivial computation, namely to evaluate postfix expressions. We have also shown the use of maybe for more robust implementations, especially when we define functions inside modules.